Welcome back to Arxflix. Today, we're exploring a fascinating new paper titled Neural Network Diffusion, Generating High-Performing Parameters with Diffusion Models. This research delves into the surprising capability of diffusion models, traditionally used for image and video generation, to create high-performing neural network parameters. This figure highlights the connection between diffusion models and neural network training. Both processes involve transitioning from random noise or initialization to specific distributions. The top illustrates the standard diffusion process in image generation, while the bottom shows the parameter distribution of batch normalization, BEN, during CFR 100 training with ResNet-18. The authors propose a novel approach called neural network diffusion, PDIF, to generate high-performing parameters. This method leverages a standard latent diffusion model to synthesize new parameter sets. Here's a visual breakdown of PDIF. It consists of two key processes: parameter autoencoder and generation. The autoencoder extracts latent representations from a subset of trained network parameters, and the diffusion model learns to synthesize these representations from random noise. The generated representations are then decoded to produce new parameters. Let's dive into the core components of PDIF. The parameter autoencoder is trained to extract latent representations from a subset of trained network parameters. This subset is typically chosen from layers like batch normalization, which are known to have significant impact on performance. The encoder, parameterized by sigma, maps the input parameters v to latent representations z. The decoder, parameterized by rho, reconstructs the parameters v from the latent representations z. The autoencoder is trained to minimize the mean squared error, MSE, between the original parameters v and the reconstructed parameters v. The parameter generation process utilizes a standard latent diffusion model to synthesize new latent representations from random noise. These representations are then passed through the trained decoder to produce new parameters. This equation describes the forward diffusion process, where Gaussian noise is progressively added to the latent representations z over time steps t. The reverse process, parameterized by theta, aims to remove the noise from zt and generate new latent representations. The diffusion model is trained to minimize the Kullback-Leibler (KL) divergence between the forward and reverse processes. The authors evaluated PDIF on a wide range of datasets and architectures, demonstrating its effectiveness in generating high-performing parameters. Across various datasets, PDIF consistently achieved similar or better performance than baseline methods, including ensemble averaging of original models. Ablation studies revealed several key insights. The number of training models significantly impacts the stability of generated models. More training data leads to better stability. Generating parameters from deeper layers tends to achieve better accuracy than generating parameters from shallower layers. Noise augmentation during autoencoder training plays a crucial role in generating stable and high-performing models. The authors investigated whether PDIF simply memorizes the training data or generates truly novel parameters. Similarity metrics showed that generated models exhibit significant differences from the original models, indicating that PDIF is not merely memorizing. Visualizations of latent representations further confirmed that PDIF generates novel representations, while adding noise to the original representations only produces interpolations. This research opens up exciting possibilities for utilizing diffusion models in parameter generation. PDIF offers a promising approach for creating high-performing neural network parameters, potentially leading to faster training and improved performance. While PDIF demonstrates significant potential, there are still challenges to address, such as memory constraints for large architectures and the need for further exploration of structure designs and performance stability. This research encourages further exploration of diffusion models in various deep learning tasks, potentially revolutionizing how we train and optimize neural networks. Thanks for watching Arxflix. Don't forget to like, subscribe, and share this video with your fellow deep learning enthusiasts. Stay tuned for more exciting research summaries. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.